Okay, to talk about Lebesgue integral, first we do some revision about the Riemann integral, which is the basic integral that you use in calculus work, right? So for this kind of Riemann integral, the idea is very simple, right? So basically you have some function like this, right? So let's say you have, just to make it a simple example, so you have, let's say a triangle, right? Triangle on a square. So I know that the area under the curve for this triangle is under curve is equal to 1/2, right? It's just half of the square. So of course this is fx equals to x, right? Okay. So in traditional Riemann integral, you want to find this integral, right? So where this is a and b, which basically refers to the area under the curve, right? So in this case, our integral is from 0 to 1 x dx, right? And since all of you are pretty good at mechanical manipulation, so everybody knows that mechanically you do it, you will get something like this, right? Now, of course, the reason why you're able to do this kind of mechanical things is there are several reasons. Okay, so so basically, this one is this operation is entirely based on the fact that if we, the connection between the integration and differentiation, yeah. So this if you integrate, you produce a function that if you differentiate, you will get the integrand. Okay, so that allows you to develop the mechanical aspect of integration. Okay, so that's primarily Newton's contribution, right? So all these things that you are learning, the mechanical part of it is because of Newton, yeah. So he discovered that these operations are valid. Okay. Now, so Riemann actually was much later, a person who came much later, right, in the 19th century. So he looked at the integral and said, well, instead of looking at it as some kind of looking at integration and differentiation as some kind of a related operation, why don't we look at it as a kind of a geometry, right? Geometrical problem. So his idea was like this. So if you have this integral, right? So you want to find area under the curve. Now the first thing is not to immediately start thinking that you can find it. Okay, the idea is to start with approximations, right? So you ask yourself, how can you find an approximation to the area under the curve? And the easiest way to do this approximation is to use something that you can calculate easily, right? So basically this would be in the form of a rectangular bar, right? Because rectangles, the area is very simple. It's basically just the width multiplied by the height, right? So here you would, as a crude approximation, you would start with something like this. Okay, you can cut at 1/2. All right, and then you after you cut at 1/2, so you project a line from 1/2 until the function, and then you make a horizontal projection to the y-axis. Okay, so then this gives you two rectangles. And of course, if you sum these two rectangles, it won't be exactly equal to, so there are these extra bits, right? So, but you don't think of it as something that you want to achieve right at, immediately, okay? Just think of it as a kind of approximation. So the approximation here would be the width is 1/2, and the height here is 1/2, right? Okay, so that's the area of this rectangle. And for the other one, that would be the base is still 1/2. The height here would be 1. Okay, so you add both of them, you get 3 So that will be, sorry, 1 over 4. This will be 1 over 2. So this will be 3 over 4. Okay. So it's definitely larger than what you know the answer to be. It doesn't matter. So the next step is we progressively find approximations, right? So we can find another approximation. So this approximation would involve, maybe you can cut it to 3 parts, right? 1/3, 2/3, right? So there's 1 part here, and 1 part here, and then 1 part here, okay? So basically then your width is 1 over 3. The height here is 1 over 3. The second height here is 2 over 3. And the third height here is looking at 1, right? So you sum these 3 rectangles, you will get, that will be 3, 6, 2 over 3, right? So it's much closer to 1 over 2 than 3 over 4 was, right? So the idea is that, well, if you progressively cut finer and finer bars, then you should be able to get very good approximations, okay? So like, for example, if you cut finer ones, right? Okay? So you keep on cutting, right? If you cut finer and finer, then your approximation will become closer and closer to the truth. So then this means that there's a connection between the area under the curve with a limiting process, right? So first we will produce a general. So we will first, let's say we divide this to intervals of 1 over n, right? Okay. So my sequence will be 0, 1 over n, 2 over n, 3 over n, until n minus 1 over n, and n over n, which is 1, right? Okay, so I have these points. So these are the points where I have a cut, right? So since this is fx equals to x, so the function here will be, so basically you're not starting from the first one, but the second one, right? So your height will be all this, okay? So this general form is I over n, where your I is from 1 until n, all right? So that will be the height, and the base is 1 over, so your base is equal to 1 over n, okay? So this means that your total rectangular bars will be, so the sum of, okay, so your sum of all rectangular bars will be equal to the base times the height. The general height is I over n, right? And you sum over all the i's, okay? From this one is summing from 1 until n, right? So basically you have 1 over n squared sum I from 1 to n. Okay, so then this gives you 1 over n squared times n plus 1 over 2. Okay, which is we simplify again, n plus 1 over 2n. And in the limit, this will tend to 1 over 2, right? We'll take limit n plus 1 over 2n. When n is large enough, it will be n over 2n. Well, when n is large enough, plus 1 doesn't matter. So this is this is like large n, right? So then you cancel off the n, so you get 1/2. Okay, which is the agrees with what you obtain using a geometric using the fact that it's actually a triangle, right? So this is the idea of Riemann integral. Okay. Yeah. So so then we have come quite a long way from Newton to Riemann, right? Right, in terms of how integration actually works. The contribution of Newton is mainly to develop the mechanical aspect of performing the integration, but to understand the behavior of the integral requires more theoretical development. So Newton didn't quite develop that. So Riemann developed this theoretical aspect. Okay. So the integration that you are actually doing routinely for calculus is actually a mixture of Newton and the mechanics is based on Newton's all the rules discovered by Newton, but the theoretical underpinnings are based on the Riemann integration, right? Which is basically a limiting process of approximating areas for the area under the curve. Okay. All right. Okay. So, by the way, is it clear to you that over here I put the sum? The sum here is equal to this. Is it clear to you? This is a basic result in discrete mathematics. Yeah. Is it clear to everyone, this result? Is it clear to you that if you are shown shown this sum, you know how to write it immediately as this term?
Yeah, I think so.
How do you know that this is equal to this? I mean, like short of memorizing it, of course. How do you know that it's equal to that formula? Can you recall immediately this formula? Or do you need to check some formula sheets for this? Feedback from everyone. Just want to check the situation among you.
I think yes, maybe.
So how do you get that?
I mean that I'm just using memorizing because this thing is like a very familiar thing to us, right?
Have you ever wondered why the formula is like that? Okay, maybe this just a
Is it because of arithmetic series?
yeah, it is an arithmetic series. But is it clear to you that why this is so? The formula is if you sum from 1 to n, you will get n plus 1 over 2. Of course, if you want to do this, I mean, if you want to show this like analytically, the usual way is, of course, to do some trick like this, right? Then you have let me see. Then you reverse it basically. I think you write it the sequence in reverse, right? So you add both of them, you will get okay. But there are n of them, right? So basically this is just n plus 1. So your S is n plus 1 over 2. This is how I mean, if you like this kind of you are some kind of algebraic person, you like to push things around, then maybe this is for you. This is a justification, okay? But I give you a very simple. I always like to approach this kind of problem from a geometric point of view, right? This kind of approaches is a little bit abstract. The geometrical approach is actually much more intuitive. So yeah, I will show you. Once you know this geometric approach, right, you will never forget this formula. Okay, so the idea is like this. So you build a ladder like this. Okay, so there's one box here, 2 boxes, 3 boxes, 4 boxes, right? Until you have the base here will be n boxes lah, right? Okay, it's just like some kind of a staircase, right? So basically, when you want to sum 1 to n, is basically you add up all the you're basically adding up all the boxes here, right? Okay. Now, if you think of it, if you have some imagination, you can think of duplicating this staircase and then reverse it. When you reverse it, you can actually stack it onto the, okay, you stack it onto, it's just like some kind of, I don't know, have you played Tetris before? Do you know a game called Tetris?
Yes.
Oh, okay. Well, Tetris used to be so like you have all these kind of blocks where you can manipulate, and then you kind of like try to fit them, right? So this is something like Tetris. If you don't know Tetris, that means you're not old enough. Okay. People who are like above 40, they all know Tetris, right? Because that was the kind of a very popular game back then. So okay, so if you invert it, you cover, then you're going to get a rectangle, right? Where the height here is n, because you got there are n, the height here is n, and then you have got one extra block here, right? So the total number of boxes in this rectangle is n plus 1, okay, times n. But you only want half of it, so you divide by 2. That's all. All right. So that's the geometric intuition for this formula. And in fact, there are also geometric formulas for this, geometric intuitions for this formula. This is n plus 1. 2n plus 1 over 6. All right, and the usual way this is actually shown is using the very boring induction method. It works, but sometimes you wonder like how do, because in order for induction to work, you must propose a result here. And the reason why induction is kind of like not very stimulating is because the question is how did you actually get this formula? Well, but once you get the formula, induction is a very powerful tool to formalize the result. But the question is how do you arrive at this formula at the beginning, right? So there is actually an intuitive, there's also actually a geometric proof for this part. Okay, so maybe maybe later when I find it, I can share it with you. Okay, once you know this kind of geometric proofs, right? You will actually you can actually recall these things very easily, because for you this means this is basically half of the area of a rectangle. Okay, and n plus 1 is this rectangle. Okay, you're taking half of it. So basically this corresponds to some kind of geometry. Okay, so I'm just sharing a bit of these side things with you. I mean, like some of these things, especially at the elementary level, they have very nice geometric representations. If you can see the problem from this geometric point of view, then a lot of your it's very helpful later when you study more abstract things. Yeah, because the geometry helps a lot. Okay, so that's the part about Riemann integral, right? So now I'm going to ask you one question here. Suppose you have a function, right? Fx is equal to 1 when your x is when your x is there's a whole bunch of drop down things that is obscuring my screen now. Okay, anyway, so you basically define some function like this, where your x is actually a rational number inside 0, 1, okay? And this is elsewhere, yeah? Okay, so I define a function like this. All right, when my x is inside this is a rational number, I give it a 1. Otherwise, I give it a 0. This is an example of an unsketchable function. In principle, you can't really sketch this function because, okay, just to see why you can't sketch this function. Okay, so suppose let's say you look at 1, right? Okay, there are only 2 things, 1 and 0. Okay, let's say you plot 1 here, and the rest are 0. Sorry. Okay. Now, but it says that your x, this is only 1 when your x is actually a rational. So for those at those points where they are not rational, right? So there are many points. So these points are not. There are many points that are not rational. There are infinitely many points, right? You will actually dig out this. You will dig out the hole here and then you put it here, isn't it? Right? Because at those points where they are not rational, so you dig away and then you put here, right? So basically, you dig out infinitely many points away from 1, right? So you basically cannot actually see this line. There's a line here, but it's full of holes, yeah? So basically, that's why we say that this is an unsketchable function, because you are digging out infinitely many points, and there's no way you can actually sketch infinitely many points, right? So I give you this function, and then I ask you, what is this? What is this integral? By Riemann's definition. Okay, so clearly, you're going to run into problems if you try to apply Riemann's definition, because you have to divide the interval where you're interested in obtaining the integration to to different. You have to partition them, right? But you cannot seem to find any reasonable partitions. Okay, you basically cannot find the partitions along. Let me see. Someone is trying to come in. Okay. So you basically cannot find any intervals such that you can actually construct the rectangular bars, right? And use that to approximate. You can try it, but you will not be able to find it. Okay. So Riemann's integral fails here. So we call it not Riemann integrable. Okay. That means you cannot find the integral of this function using this way of doing integration. All right, it's starting to feel a bit weird already, right? Oh, there are functions that you can't do integration. So the idea is that, well, it may actually depend on how you define what an integral is. It turns out that there are actually many ways you can define an integral. Yeah, what an integral actually means. So if you use the appropriate framework, you can find an integral for this function. All right. So the framework that we are going to study today is called the Lebesgue integral. All right, and using Lebesgue integral, we are going to show that the integral of this function is equal to 0. Okay, but first we need to define what Lebesgue integral is. Yeah. Okay. So Lebesgue integral works like this. So you have let's say I have some kind of arbitrary function. So doesn't matter. Let me just sketch an arbitrary function. Maybe something like this. Okay, just an arbitrary function f x. Sorry, this is my f. Okay. So this is my a, and this is my b. Okay, so I'm going to do something like this here. Let me see. Okay. So I'm going to make so I'm going to make partitions like this. I'm going to start somewhere around here. Okay. So you see that instead of actually like the Riemann will start partitions on the x-axis. For the Lebesgue, the partitions will start actually on the y-axis. Right? So I can define a few partitions like this. They need not be of equal length. They can be of arbitrary lengths. Okay. Okay, maybe like this, right? Okay, so now for this part here, I'm going to find the, let me see. So, okay, maybe not this one. Okay, maybe not that one. Okay, so from here, I'm going to, okay, so over here, I will make a projection. Okay, and then I'll make another projection here. Okay, the projection here. Let's see, make a projection here. Okay. Or maybe I go by, do the projection one by one. All right. So maybe clearer. Okay. So once you make a projection like this downwards, right? So I'm going to, so here we say that we have a set, let's say A1, right? So this interval here, all the points from A to, so within A to this boundary here, we call this, the sets here contained in, so the points here are contained in set A1, right? And then over here, I'm going to make a rectangle like this. Okay, so this rectangle, I'm going to, so for this interval, right, I'm going to take the infimum of f of x. All right, where my, so my x is in A1. Okay. Right. So let me repeat. So I first I draw a horizontal line right across the graph, and then at the point where I have an intersection, I make a projection downwards to the x-axis. Right. Then starting from the leftmost limit, I go all the way until that point, and I construct a set A1. Right. And then for the height, I will take, so within the all the values in set A1, I will take the infimum, right? So the function will be from here to here. So the infimum will be the tail here, right? Okay. And then let's look at the second one, right? So the second one, let's say I make a cut like this. Okay. So I will have, again, I make a projection down here. So this entire interval here, I will put everything into a set A2. And then I will take the infimum, yeah? The infimum of this function over A2. So that will be the smallest one here, A2, right? It's this point. So, and then I construct the rectangle here, okay? And then we will have, let's say, this point here. So over here we have a 3, right? So the function is going from here to here, and the infimum will be actually here, right? So then the rectangular bar will be like this. All right, and then over here we have this partition. Let's say we can come here. So that will be my A4. And so over this interval, right? Over this interval, my infimum is actually here, right? So my function is crossing from here to here over this interval. So the infimum is actually here. So I will put it here and then construct the rectangle like this. All right. And so on and so forth. Yeah. So I have another one here. So there will be my A5. So the infimum will be here. Construct like this. And then I have this one. So A5, that will be my A6. And then infimum is over here. All right. And then I have this one. So my, yeah, so this will be my, just to make it simple, I'll just stop here. So this will be my A7. So the whole thing. So I'm just going to remove this line. Okay. Okay. So basically, so you can actually approximate the area under the curve with all these rectangular bars, right? You just add up all these rectangular bars, this rectangular bar, add everything. Of course, it's not perfect, right? You still have some gaps over here, but it doesn't matter. You're just trying to work out some kind of approximation first, okay? So how do we actually describe this approximation? This approximation will definitely depend on the base here. So the base here is actually a set, right? So we have already learned measure. Okay, so we are going to, so this is a set. So the so we're going to the length here. So we are going to take the measure of a set. So this is for any general set here, right? So the I is running from 1 until 7 in this case, yeah. So the mu of AI is basically measuring is basically providing a measure of this set, okay. And the height will be basically this one, yeah. The infimum of F. So over here, I'm going to use a slightly different notation. So I'm going to put omega here. So omega is in AI, okay? Basically, this one is just to talk about, so over an interval, so you have your function here, right? You are taking, so this function here, you're taking the infimum, okay? So in this case, if you have this stretch, the infimum is here. Just now I have this stretch, right? So my infimum is over here, okay? So it's just like that. There's nothing complicated about this part, all right? You're taking the smallest of the f of x over values of x in some set, okay? So when you multiply together, this will give you the rectangular bar, yeah? So this will give you the area of the rectangular bar. Okay? So then, of course, if you want to add up everything, so we sum, right? Okay? So the approximation of the area under curve is given by the sum, okay? So mu of AI times infimum of f of omega, where my omega is in the set. Okay, so this is geometrically is the area of rectangular bar. Okay, and then this one you just add up everything, add up all bars. All right. Now, so obviously, that if you make different cuts, right, you will get different kinds of approximation, isn't it? For example, if you start cutting, if you make different cuts, like if you cut like this, if you make a lot of very fine cuts, okay, and so on and so forth, different cuts will give you different approximations, right? So we are interested in a particular cut that will actually make this as large as possible. So we say that we want this thing. We want the supremum. We want the supremum. Oops. We want the supremum of this approximation. All right. So the supremum of this approximation, because clearly, if you have different partitions, right, you'll get different approximations. But we want the one that is as large as possible. The one that's as large as possible will have everything filled up. Okay, you just need to choose a suitable partition. Yeah, so you'll fill out everything. So that will be exactly the area under the curve. Okay, so this is the definition for the Lebesgue integral, and we write it like this. Okay, it's different from your Riemann integral, because over here is d of mu, where this mu represents your measure. Yeah, so so when you see some integral that's written in not in dx but in d mu, where this mu is the measure, you know that they are talking about the Lebesgue integral. Okay. All right. Okay. So this is the definition of the Lebesgue integral. Do you have any questions about it? If there's nothing, if it's not clear to you.
I'm still not really understand how this thing different from the Riemann integral.
Later you will see, but it's just a different. Okay, so this your Riemann integral is actually taking partitions on your x-axis. All right. Let me clear this board. So let's say, go back to the example of the triangle. So if you do Riemann integral, basically what you're doing is you're making partitions on, you're finding partitions here, right? On your x-axis, let's say 0, 1. And you're basically trying to approximate it using the rectangles here, right? And we already showed just now that your rectangular bars will have, this will be the width of the rectangular bar. This will be the height. Okay, so basically when you multiply, this will be the area of rectangular bar, right? And then you add up all of them. Okay, so then this gives you until n. So n plus 1 over 2n square. So this will be n plus 1 over 2n, right? So your Riemann integral is equal to the limit of n tends to infinity for n plus 1 over 2n, which gives you 1 over 2. All right. So that one is actually straightforward. Yeah, it's a limiting process. Yeah, you add up all the rectangular bars and then you think about cutting them as fine as possible. This is very straightforward. Now Lebesgue integral is a bit more abstract here because it doesn't start with partitions here. It starts with partitions on the y-axis. So for the same thing, right? So the way it does it is like this. It may actually choose to cut like this. Then maybe it choose another partition here, maybe another partition here. Okay. So for this, you will have, so this partition will, so this line here will intersect your function at this point. So you drop down a projection here, right? Okay. So then this will be your A1 set, right? Now, for this function here, the infimum is here. So you basically have nothing here. Okay, you basically have no height here. Okay, and then for this one, the second line here, so you come to this part. So the interval that's over here is A2, and for this function here, the infimum is at the endpoint here, right? So your rectangular bar will be defined by this bit. Okay. And then you come for this partition, so it will come to here. So this will be your A3. And over this function here, the infimum is here. So your rectangular bar will be this one. Okay. And finally, for this set, right, A4, this is 1, yeah? So over this interval, the infimum is here. So your rectangular bar is here. Okay, so basically, if you use, so this is one of the approximation that you can do, yeah, for the triangle. So therefore, again, this one will come to summation of mu of AI, okay, times the infimum of f of omega. Okay, so your mu here is basically representing the measure, right, of this set. If this is absolutely continuous, then it's just equal to the length, yeah. Because if you have a absolutely continuous interval, the measure of that interval is just its length, okay. But the measure is actually more general, right? For example, if you have a countable set, the measure of a countable set is 0, okay. So the measure is actually something more general than the length. Okay, so you have over here, this will be the base, and then you have a height, right? The height is basically you take the infimum over the function, right? For values of omega that's within that particular set, okay? So this product here gives you the area under the rectangular bars area, rectangular bar area. Okay, but these rectangular bars are induced by cuts on the y-axis rather than on the x-axis. Okay. So and then this is one of the approximation. So the Lebesgue integral will be the supremum. All right, the sup of this thing. That means I will find some cuts that will actually make the area under the curve as large as possible. And of course, when it's as large as possible, it's just actually equal to the area under the curve. This is basically more conceptual. You will find later that actually, based on this, it's actually a concept, but when we try to find the Lebesgue integral, we will make use of some regular ideas in the Riemann integral. Okay, but it is, for starters, it's actually a concept, because here you are just saying that you will find a partition that will maximize this thing. So we just say the sup. right? The supremum. So this is my Lebesgue integral, which I will write like this. So for example, this one I will say so here I will write like this, right? This is Riemann integral, right? But here I will write it like this. Okay, when I write it like this, it means I'm thinking of it as usually they might actually include something like this, a measure, right? But usually they'll just leave it as d mu, okay? So this is a Lebesgue integral. Both of them are trying to give you area under the curve, but they are starting from different kinds of ideas, all right? So this is the part that we want to look at. One is thinking of partitions that are made on the x-axis, which is more natural. This one is thinking of partitions on your f, right, rather than on your x, okay? So when you cut on the f, it induces a set on the x. Okay, this is the main difference. Because your sets here, later you will see why this is actually more useful generally than this part. Because this part here, right, they cannot deal with when you have the situation just now, right, you have a function where it's full of holes. Then you find that this way of trying to find a partition is questionable. There's just no way you can find these partitions on the x. But you will be able to find sets where you can have measures if you use the Lebesgue integral. So I'm going to talk about that in the next hour, right? So how to actually deal with such types of integrals. But for starters, is it okay for you, the idea of how to do these partitions?
Doctor, the mu is just simply the length, is it?
Is a measure, it will depend on what your A is. Like for example, if let's say you have mu of, let's say, an interval like A to B, right? The measure of a length, this will be just, of course, B minus A. But if this is a set, right? An interval is a set, right? If you mu a set where it is something like this, it's a countable set, yeah? The mu of this is 0 because the mu of the measure of a countable set is 0. Okay, when the set is countable, even though it's infinitely large, the measure is still 0. Because I think we already know this, right? From the Lebesgue integral. So we know that the Lebesgue measure, here you can think of it as a Lebesgue measure, right? You have a Lebesgue measure, let's say on the closed one, and the Lebesgue measure of the half open is also the same. They are equal to the length, right? So therefore so you see your AB is basically the singleton A union the half open set, right? And since this is disjoint, so you can write it like this, right? And since this is completely closed, it's definitely B minus A. So this is again B minus A, and therefore you show that the Lebesgue measure of a singleton is actually 0, right? Okay, and if you have a countable set, right, doesn't matter. Your countable set is basically a countable union of singletons. Okay, your countable union of singletons, and each of the singletons here have 0 measure. So the measure of a countable set is definitely 0. All right. So it depends. Yeah. When you put a measure here, it will depend on what is the content of your set. It need not always be an interval. The measure need not always be equal to the length. It can be actually something else. It can be 0. If your set is actually countable. Okay. Any more questions from other students? Is that clear to you?
Yes, clear, Doctor. Thank you.
Okay. Right. So let's take a 10-minute break for some stretching. Then we come back. Then I'll explain to you how to use Lebesgue integral to solve the problem just now. Yeah. So the problem that we're going to talk about is just now was the f of x equal to x is in a rational number that's in 0, 1, and this is elsewhere. So this is the unsketchable function. Okay, and we can actually, so this does not exist, cannot not Riemann integrable. But yes, we can find a solution for this. Okay, so we come back and we will see what is this solution. Okay, right, so okay, so although this function is actually not sketchable, so we will just pretend that we can sketch it. So basically it is like this. So basically then you drop holes on, you dig out holes here and put them on 0, right? For those kind of values that are actually not rational numbers, right? Now, so if you think of a Lebesgue measure, right, Lebesgue integral, so basically you have these components. Okay, so this will be the measure for the rectangles, right? Now, first I want to ask you, right? So for those, let me see. So okay, so basically you have this line here. You just need to have one. Just to have this line here, right? Cutting the function. Okay. So the first observation is that the infimum of fw, right? Let me see. It will be 0 or 1. Okay. So now, how about the measure of AI? Now, if you look at this set, right? Now for this set here, those are the ones that actually remain on this line, yeah? Okay. Those the rational numbers. They remain on this line, okay? So their infimum will actually be 1, yeah? Because it's a constant line, so the infimum is just itself, right? It's 1. But how about the measure? You look at this set here, right? This set is a countable set. Okay? So a countable set will have what measure? So this will be the set where Q is in 0, 1. So this set, the measure is 0, right? Since A1 is countable. Okay? So 0 multiplied by 1 will give you 0. Okay? On the other hand, those that are elsewhere, right? Those that are elsewhere, they are all here already, okay? So their infimum is already 0, all right? And then their infimum is already 0. And then this set, it doesn't matter whether they are countable or uncountable, all right? So 0 multiplied by anything else here will give you, they are definitely not going to go to infinity. So 0 multiplied by 0 or some constant here will give you 0, okay? So either case, you will actually have 0 measure, all right? And therefore, the answer for this Lebesgue integral is 0. Okay? So, so this is actually a very pathologic. This is actually a very unusual example where, of course, in practice, we are not going to, we don't have this kind of things to worry about, but it's a nice example, yeah, of being able to define what an integral is for some unusual functions, okay? And in fact, so once we have this way of finding the Lebesgue integral, we can actually extend it to some idea called almost everywhere. We call it integrable almost everywhere. Okay. But first, before that, are you okay with this explanation? Why the Lebesgue integral of this function here is equal to 0? You can see, you actually can see the main power of the Lebesgue integral comes from this part here, the measure of the set. And this, it happens that for the set that you're interested in here, this is actually a countable set, so the measure is naturally 0. Okay. Are you okay with this example?
Yes, doctor.
Okay. So let me move to this idea of integrable almost everywhere. Okay. Um, okay. So now when you have a function, right? Okay, so if we say something like this, f and x converges to f almost everywhere. What does it mean? What does this almost everywhere mean? It means something like this. So suppose you have this. So this is your f, all right. So you may have your f. So this is your fn. So your fn is so you may have some f5, f6 or whatever, right? So in the limit, your fn is actually in the limit is actually your f is converging to f, right? Now I introduced the word almost everywhere here. Why? It could happen that at certain points, right? There are certain points here where it doesn't converge to f, but it actually goes to like maybe some weird points. It doesn't matter. It can be some arbitrary points like this. But on the whole, right, your fn is actually equal to f, right? You say almost everywhere means it doesn't matter. Like other parts, they may be weird like this. They may have something like this, except that you don't really care about them because the measure of this set, right? Let's say I collect this A. So all this will go into the set A, okay? And it has to be countable. So A is countable. So the mu will be 0 because it's countable, all right? So it doesn't matter. So your fn can converge to f almost everywhere, meaning that it doesn't have to be, if you say that fn converges to f, right, it means that this has to be true. These things cannot happen. It has to be like the whole thing is on f itself. But when you say fn converges to f almost everywhere, it means that there could be some points here whereby your fn doesn't converge to f, but it converges to some points like this. But you don't really care about them because the measure of these points, right, where it's actually not f, is actually 0, okay? That's what we mean by almost everywhere. So almost everywhere is kind of like a more general situation. Okay, if you require it to converge to f without this general condition situation, that means you cannot tolerate this kind of situations. Okay, it turns out that we can actually tolerate these situations because the measure is actually at 0. So our integral will be well defined, right? So for example, if you integrate f, right, the f dx. For example, if you take the Riemann, right? So this is your f. Okay. Now, if like just now the example, right? You have too many holes. If you got too many holes, this is not defined, right? Yeah, like the example just now. Yeah, you got even a constant function. If you got too many holes there, it's actually not defined by Riemann. Okay, definition. However, if you do the Lebesgue, it's actually defined. Okay, so if you have a lot of holes, like the case just now, so your Lebesgue integral is basically just 0. Okay, if you have if you for almost everywhere, so you only maybe have at only a certain points here. So then your Riemann integral, let's say your f is 1 here, right? So there are some points here where you dig out, but you put maybe it's something like that. Then the Lebesgue integral of f d mu will basically be equal to, let's say if you just do until 1, yeah, it will be equal to 1. Yeah, because let me clear the board. Okay, so like in this case, right? So you can actually, so you make a partition, oops. You make a partition. So here is actually quite simple, right? So it just goes like this. Okay. So your, so you will have basically your mu of AI is equal to this length, right? The mu of 0, 1 without the, let's say those singletons, yeah, let's say 0.1, let's say this is 0.8, right? Okay, so this measure is still 1, right? Okay, because this part here, right, 0, 1 without 0.1 and 0.8 is equal to 0.1. Sorry, union 0 to 1 is equal to, sorry, union, this one, if you union the singletons here, you take union. So this set union, this will become 0, 1, right? Okay. So you take the measure of this set is equal to measure of this interval, right? And since these two sets are disjoint, so you will have the measure of 0, 1 without the 0.1 and 0.8. Is equal to the measure of 0, 1, right? And here this is just 1. This is a countable set, so it's 0. So over here, definitely this is 1, right? 1 plus 0 equals to 1. So the measure here is actually 1. And the infimum is the infimum of f of omega, where my omega is in A1, right? In this case, my A1 is equal to 1, right? Okay, so it will be 1 times 1. All right. So that will be 1. Now, if you have other partitions here, you make a partition over here. You partition here, partition here. You can also do that. You notice that when you do this, so the projection is here, right? So basically here, so you have this point, right? But this point is just some value here, right? So the infimum of FW is actually some constant. But the set that it falls on, right, is a singleton. So the measure of 0.1 is 0. The measure of 0.8 is 0. So these 2 points, right, they contribute nothing to the integral. Okay, they contribute nothing to integral. So therefore, the area under the curve is basically you don't need to be bothered by these holes. Yeah, these holes don't bother you because they basically have 0 measure. All right, so so this gives you this idea about almost everywhere. Almost everywhere is always related to having zero measures at countable sets. Okay. So let's look at a few more examples. So so another example here. So perhaps you have your some distribution. Let's say an exponential distribution. Okay. Now, of course, in usual probability theory, so you have your fx. Your fx is equal to this function, yeah. And your Lebesgue integral. So your Lebesgue integral will be equal to 1, yeah, because basically when this is well behaved, your Lebesgue integral is actually equivalent to your Riemann integral. Actually, the way to write it would be like this. Actually, generally, it is not. We don't actually write the limit of integration like what we do in Riemann, okay? Because this is kind of like, yeah, I shouldn't write the limit here. Okay. So if let's say you have a few holes like this. Okay, so if you define your fx to be the following, yeah, is the values of x in the positive real line without the, but you dig out 1, 2, 3, 4, 5, right? It's not, it's actually defined as 0 at those points. So one example will be like you dig out this point and you put it here. You dig out, this is 1, yeah. So 2, you dig out, you put 2. 3, you dig out, you put here, and so on, right? So this function has got a lot of holes, but of course, definitely here your holes are not as so you can still sketch this function, yeah, because most the holes are not as many as the case of the rational numbers there that you have. Okay, so you have this, yeah. So you can still say that we will say that fx equals to e minus x almost everywhere. Okay, because most of the time it means that most of the time your fx is basically just your ex, except at so that means it is fx equals to ex at all points x except at those sets of x with zero measure. Okay, so it doesn't matter even if you put down holes like this. The integral, in this case, when you take the integration, you would take the Lebesgue integral, right? That's much easier because then this would basically be just like, for example, you put a line over here. Okay, you put this partition over here. Well, in fact, if you don't put it at 0, you put it somewhere else here, it is still the same. Okay, even if you don't put it at 0, maybe I put it at some non-zero place. Right? So it doesn't matter. Your infimum here will be a constant, but since this set is actually a countable set, so its measure will be 0, right? So it adds nothing to the Lebesgue integral. Okay, because your Lebesgue integral is actually very highly dependent on the measure of the sets. Okay, so over here you definitely, like, for example, you can have a partition here, so the infim, so you have one bar here, right? So you can make as many partitions as you want, right? So you can think of it like that. So definitely the Lebesgue integral, so at this point there's at this point there's nothing there, right? So you don't have to worry. So there's nothing over here. So there's nothing here, right? But over these points, you can actually have your rectangular bars, right? So therefore, your Lebesgue integral is equal to definitely the sup of this sum, right? The sum of the measure and the infimum of the function, right? Generally just denoted by I, okay? Okay, so this is what almost everywhere means. And now I just give you some, maybe we just talk about some basic properties of the Lebesgue integral. So we have the so-called positive part and negative part. Okay, so you basically have integral Lebesgue integral. I can write it like this. Okay, so what does this mean actually? So the definition is like this. So, okay, so your function can go to the negative side, right? So then the question is, when you have something like this, how do I do the partitions? Okay, because in Lebesgue integral, you do your partitions like this, right? Okay. So to make it simple, we will, this whole integral, so we are interested in the area under the curve here. Yeah. So then we consider something like this. This is just the positive part. That means we will only sketch the function where it's positive. So this part, there's nothing here, 0. And then over here. Okay. So this is my f plus. So my integral of f plus is here. Okay. And then I have f minus. So f minus is basically this part, but I flip it up. I flip up to the positive side. Okay. You take the negative part, but you flip it up. Okay. So this will be my f negative. Okay. So so this area under the curve here will be this integral. Okay. So therefore, the integral of f d mu the general one, will be equal to the positive part. You take the Lebesgue integral over here, then you'll subtract the Lebesgue integral from here, right? Of course, you can get a negative number for that. Okay, but then this becomes well defined, yeah, because this is all, then you can partition like this. Okay. Okay, and then you can get your rectangular bars. Okay. So this just, this device turns out to be important because it can help you decide sometimes whether there are some, okay, there are some functions that are Riemann integrable, but not Lebesgue integrable. Okay, so this later we will look at some examples. Yeah, what are these examples where it's not Lebesgue integrable? Okay, it turns out that it's because these parts they already diverge. Okay, so although when you do the Riemann it converges, but when you do the Lebesgue it does not, right? So there are also some weird things that arise with this kind of definition. So what this is to tell you that the definitions that people gave in order to define what an integral is, right? They always have some pathologies. Okay, pathologies as in there will be always some situation where they have some weird behaviors, right? The point is that if most of the time they are behaving more or less appropriately, okay, for the usual cases, then we find them useful. All right. So if you combine the Riemann and the Lebesgue integral, the use kind of like together, then it solves a lot of situations that you commonly see in probability theory. Okay, so I think yeah, so it's almost 12:50. So I think we will just stop here for today. This may be a bit abstract for you for today. Yeah, the contents. So later I will post up the lecture notes. Yeah, they're not ready yet. Okay, so maybe you check back spectrum later. All right. Okay, so that's all I want to talk about for this week. Before we close, are there any questions from you?
It's like for Riemann integral, we can find the exact value for the function, right? For the area under the curve of the function. So for Lebesgue, is it only a approximation?
Sorry?
Or we can actually for Lebesgue integral, right? Is it only an approximation, or we can actually find the exact value for the function?
Okay, if your Riemann integral, right? Most of the time, if your function is okay, there are some functions that you are not able to integrate from a Riemann integration point of view. All right, like the example that I showed just now when you have too many holes. That one, the Lebesgue integral can solve the problem very easily. Now, most of the time, if for well-defined functions, right, you will use Riemann integral to do it, okay? in those situations, your Lebesgue integral and your Riemann integral, they are exactly the same thing. Like for example, you have the usual case, right? This one just now, right? This one you know that it is this, right? Okay, just now the area of the triangle. So if you do Riemann integral, this is also equal to 1/2. But so the way to do it is, of course, because the Riemann idea is actually conceptual, because it takes the soup, right, of the sum, okay, of the measure. So it's actually, it doesn't give you an operational way to do it. But that's why I say you combine both of them, because when this is well behaved, right, you will find that this is exactly equivalent to, it will be equivalent to the Riemann integral. And therefore, you can just use the mechanism of the Riemann integral to obtain the result. So it's kind of like when for well-behaved functions, right, you basically, when you do the Lebesgue integral, you just connect to the, it's basically just your Riemann integral. So that's the nice part. So it's only when your Riemann integral has difficulties, yeah, your Riemann integral will sometimes get into difficulties for those kind of problems where you have too many holes. So in that case, your Lebesgue integral can come in and save the day. And usually the Lebesgue integral in those cases, right, they will give you some very simple kinds of measures. All right, like sometimes like just now you saw, right, it's actually 0. And that actually you can find that from the, by considering the definition of the Riemann, the Lebesgue integral. Because the only way you can get some calculations out from this definition is that this part here is actually going to some simple numbers like 0 or some constants. Because here you take soup, you see. So if you don't have, so generally it doesn't provide you with any mechanism. It's like a conceptual tool, right? And it can help you solve some conceptual problems with general sets used in integration. But to evaluate the exact value for usual cases is basically just the same as your Riemann integral. So we look at a few more examples. Maybe that will later, maybe in the tutorial, then things might be clearer to you. Okay.
All right, thank you, Doctor.
Okay, so I think we will just call it a day here. All right. So thanks for listening.